Hey, Dr. B here again, and let's take a look at the arrhenius equation. This is the only equation you'll see that allows you to directly calculate the activation energy, E sub A, for a chemical reaction. That's the hump you got to get over in order for a reaction to occur. Usually it's expressed in not very useful formats. I've rearranged it here so we can plug in directly to solve for the activation energy. And it's equal to the natural log of K's at two different temperatures, that's rate constants at two different temperatures, times R, an energy source for R, which is given here. And if you have enough data, it should be directly plug-in. Notice you got to use Kelvin for your temperature. And so here's a typical question, which is direct plug-in, and that's a good place to start for these. At 650 K, that's RT1, and it is Kelvin, that's good. Nitrogen dioxide decomposes into nitrogen monoxide and oxygen fine. The rate constant is 1.66 per second. That must be our K1 since it's at T1. At 700 K, that's our T2. The rate constant goes up quite a bit actually, and that must be our K2. Find the activation energy. Well, we got everything. We got K1, we got K2, we got R even. Let's plug in and find out what happens. So plugging in those two numbers and those two temperatures and solving finds that the activation energy here is 113,000 joules per mole, which we've simply converted to 113 kilojoules per mole since 1,000 joules equals a kilojoule. That's an introduction to the arrhenius equation.